Okay, so today I would like to review the materials of the class as preparation um, for the quiz. We announced that the quiz is actually postponed to allow you basically to focus on the projects, and the quiz will happen only next week. But we would like to do the review. We'll also open a discussion page. So I'll talk about this when we get to the quiz preparation section. So the course material review pretty much follows the sequence of slides and the class. And I kind of chose to focus on the main points. You can think about this as basically potential question per slide. And most of the questions will be multiple choice questions related to understanding, not only, but mostly. So I'll kind of try to explain what I think are the main points to remember, and we'll translate this basically to the quiz questions. So a bit of giving out some of the possible question answers as I explain this, but I think that's the purpose of the review in some sense. So one thing we would like you to take away or learn from this class are the three main representations of music: annotated representation, representation using basically performance instructions like what we saw in the piano roll. And there is kind of a discrepancy between these two, because these might include a lot of timing and expressive inflections, so the velocity and changes in timing, and it doesn't have as structured information. This one can actually tell you the meter, the key, and maybe this one also has some meta information or high level information like chords. Well, these are the performance instructions, and then they're rendered actually to recordings. So audio. Data formats. This is, I wouldn't say text file necessary, but well, PDF or some musical notation files, which are much more structured, musical XML, okay, typesetting. This will be a MIDI file, and this is an audio file. And it's pretty evident, but just to make sure that you know the terminology and understand the different file formats. In terms of the symbolic representations, we spoke about, again, the notation. This is a way to consider this as MIDI file with instructions for synthesizers, not ons, not offs, different channels. So this becomes a bit more technical. We don't expect you to know exactly about the MIDI format and the controllers and the control parameters and channel parameters. Basically, we focused only on note ons and offs and the note numbers. So they identify the keys, velocities. And one thing that actually came up yesterday in one of the presentations was that here we call it note off, but really note on with velocity 0 is a note off. Okay, so there's this kind of double convention or ambiguity in MIDI. It has actually a command called note off, but if you send the command note on with 0, it will be effectively doing the same. And so just so you know about these parameters, these are notes, which notes are being played, velocity, and time. And time here is relative to ticks, so you can play this with different speeds. And kind of an equivalent, almost one-to-one translation, but still kind of more of a graphical representation called piano roll. And you can see how they translated. The velocity here is less, is less evident. You have actually to look it up. The channel, the MIDI number could be somehow coded, but so it's in some sense a partial representation of this, unless you have some additional information every note here. So yeah, understanding the channels, the messages, and the convention of MIDI is pretty essential. And this will be the piano roll matrix, because some of the files that you use in your homework use both of them. So you should understand what is a piano roll and what are the basic messages from a MIDI file. Next, yeah, kind of like, this is really just repetition. So there's nothing much new in this file, except for the fact that we analyze this in frequency, and that will be the next. So you need to know what's an FFT, but here kind of the idea is that FFTs capture a short instance in time. Actually, usually the windows are much shorter than what's represented here. So this idea of short time, so this involves in time, this involves in time, this is just a snapshot. So FFT is a snapshot. So so really, I'm thinking about a specific question. This slide basically, I don't think it has a specific question. All the questions were in the previous one, just kind of emphasizes that the short time aspect of every FFT analysis, and that will repeat itself. So going forward, we want you to understand the basic concepts of frequency, physics, but at least these basic notions are really kind of essential for doing any kind of machine learning in music and audio, but also understanding how symbolic representations is rendered into audio eventually. So just understanding that a pure tone has one frequency, and that frequency is actually is the period, or 1 over the period. Okay, so if you don't remember that from physics, I hope you kind of like have a firm enough understanding after this class, knowing that what a frequency means and how it translates to waveform. And then the second concept, which is kind of a musical, it's musical acoustics concepts of overtones, right? And I'm not actually annotating anything, so hopefully you kind of remember. Overtones means these are the multiples of the fundamental, and this is just an equivalent representation for a waveform, which is more complex than an ideal sinusoid. And we won't really go into the details of why these are multiples. You need to remember that these are multiples of them. And this is why they're called harmonics, first, second, and so on. And so this idea, harmonic, means integral or integer multiple, okay, of the fundamental frequency. The physical reason is that if this is a purely periodic waveform, where in nature they're not exactly, precise periodic waveforms, but if they are, they can show that the math only allows for discrete frequencies which are multiples of the fundamental. And basically, that's kind of a physical constraint here, that the string can vibrate with specific nodes, which would be 0. Okay, whatever. So yeah, that principle, periodic waveform, which is complex, has this overtone structure, and if it's purely periodic, the overtone structure is harmonically related, which means multiple integer multiples of the fundamental frequency. That's kind of an easy way to ask this, right? The difference between periodic or pitch and noise is the idea that noise has continuous spectrum. Pretty much just one question about this, right? So it doesn't have discrete tones. It has infinite in the sense of its continuous frequencies. Okay, not infinite in going infinite in frequency, just infinite in terms of the resolution here is infinitely precise. We spoke then about some measures of noise versus periodicity. So since spectral flatness is a very common term in extracting features and characterizing audio, also in music information retrieval, I would like you to know what the spectral flatness is. And the easiest way to remember this is not so much through this equation, it's this one. This is basically harmonic mean divided by arithmetic mean. Just remember, if you take something, you multiply this n times and take the nth root. Okay, this is I think that's the harmonic mean, right? And this is the usual average. In the specific thing that I kind of introduced in this class, and I would like you to be familiar with the concept, is the idea of information rate, which I define just as a log relations between these things. And I demonstrated this in this example. So this example was showing actually that whenever the spectral flatness is close to 1, the log of this is close to 0. That's where you have basically non-flat signal. So spectral flatness, which is small number spectral flatness between 0 and 1. Small spectral flatness means that you have peaks. you have really like standing out harmonics, so you have these peaks. While if you have spectral flatness close to 1, which is the information rate close to 0, this is a plot of the information rate we showed in class. Whenever you have noise, you see these drops in, spectral flatness close to 1, you will have noise bands, so you have drops in here, like silence and bands of noise, like this one, pretty flat band, and this is a low information rate or spectral flatness close to 1. So this is kind of a way to distinguish between structure and noise. This was then related to the idea that we followed later on of information rate or information dynamics, because both of these were basically, and I didn't provide the proofs, but as a concept, the idea of noise is something that is not predictable. And this is measured by this relative reduction in entropy. So we'll talk about entropy. So the notion of spectral flatness just as a signal measure that distinguishes noise from signal, that noise actually is much more continuous or closer to being flat, and signal have a lot of peaks. So periodic signals have structure. This can be detected with spectral flatness measure, and that it actually translates to question of ability to predict the signal. So the concept of information rate is a relative reduction in entropy. Understanding just this as a concept, even if the proofs are not there, I think this is an intuitive enough concept because it serves a lot of musical kind of motivation behind other models later on. Moving on, come on, where am I? Yeah, we presented several examples, but I would like you kind of also to know, at least point out to some musical kind of references. So we didn't choose, it's not a music history class, but you should know at least about, and you had this as one of the homework. So I'm sure everybody knows what the dice game, the Würfelspiel, Mozart's dice game was. So we can just, ask you how it works. And, I'm sure everybody knows by now what is the idea of such a game. Then we move to signal processing a little bit more in detail. Sampling theorem. Again, we didn't prove the sampling theorem, but I think this is the intuitive proof. And one thing that I need everybody to know and understand, because the fact that there is a sampling frequency to every audio file, and that you need to be able to understand what frequencies are represented there. So this concept, the concept of Nyquist frequency, which is half of the sampling frequency, and the idea of aliasing, which means that if you sample a signal which is higher than Nyquist frequency, and you can see the samples here, when you reconstruct it, you will basically reconstruct this waveform, right? Because actually you don't know this is frequency. The way the math works is that it will actually find the lowest frequencies that can still match these points. And if you go through the math, you'll see that you start reflecting these frequencies. So any frequency above Nyquist will be reflected to frequency under Nyquist with the same basically distance from the Nyquist frequency. So aliasing and Nyquist frequency. Okay, those who ever did any kind of music editing, I'm sure have encountered this. There are even effects that intentionally create aliasing because that was an artifact that existed in early synthesizers, and sometimes people even like to hear that. But for pure mathematical point of view, sampling basically is a way to take physical frequencies, and it can reconstruct frequencies up to half of the sampling frequency up to this Nyquist frequency. You had homework about this matrix, which is the way to calculate DFT. So I think, this, you're familiar now very well with this equation. You understand how it's being built, that this is the inverse of this. So the idea that discrete Fourier transform, basically matrix complex transformation of your sound vector into another vector, which is complex numbers. That kind of mathematical leap. I think understanding the intuition and how they're related is really important, because that's kind of the basis for a lot of the tools that we use later on. Even if you call the FFT as a function, that's pretty much what it does, maybe in a more efficient way. So understanding what a DFT is, and then some of these parameters. So let me kind of spell them out again, and that could be a question. So what are the parameters? The N would be the size of the sound vector, basically, that we are just only taking a chunk of N samples, that it results in N spectral bins, that the frequency resolution is the sampling frequency divided by N, and you end up with half of basically amplitudes, because they repeat themselves, and phases. And then the phases have the symmetry asymmetry issue, but understanding what are the amplitudes, which are basically the absolute of that Fourier transform, and the phases, which is, and I didn't correct the slide, it's the 8th of. Okay, I'll have to fix this. I had a note and I forgot to do this. Okay, at 10 width of. Okay. So understanding, basically these parameters and what is this frequency resolution. So you can think about a question like for FFT of size and for a signal that was sampled at 10,000 hertz, and you have N of 100, what is the frequency resolution? So you just do the math there. The next step we covered was the short time Fourier transform. So first of all, understanding and being familiar with the term short time. So it's basically Fourier transform over times. And this includes the idea of the window. So you should be able to identify, understand what's a window. Basically, it's a sliding window in time that samples it, right? And then the spectrogram, which is this operation that takes these parameters. As far as we're concerned, the STFT and spectrogram are equivalent unless we just keep the amplitudes of the spectrogram. One thing that I would like you to remember or keep in mind are the differences between the so-called narrowband and wideband analysis, which relate to the, it's inversely proportional. Long time is high resolution frequency. It's a poor resolution time, high resolution frequency, good resolution in time, poor resolution frequency. Okay, so these are kind of the examples we showed: narrowband, wideband, and the reason, hopefully kind of later on, because we already covered this, you made the link between the idea that these would be basically formats. I mean, these big areas of amplification and frequency will be related to formats. Well, these are the pitches. So you can see them both by doing Fourier transform, just depending on how you do them. We spoke about just the constant overlap condition. We didn't really ask you to do FFT and inverse FFT and modify, but just keep in mind that there are conditions for how to space the windows, which windows to choose, and how to do the hop, so that you won't have this wiggling effect. So I would like you to keep in mind what is the constant overlap condition for FFT reconstruction. Then we went and talked about amplitude spectrum and the fact that we cannot reconstruct the phase. We cannot reconstruct without the phase. And we spoke about the Griffith and Lim algorithm. So if you understand what it does, basically these steps that you actually implemented, we can just ask another question that verifies that you actually remember or understand what it is. And this is just a representation. So these two slides are basically covering exactly the same material, but I thought that graphically reminding you of what is a Griffith limb is helpful. So yes, expect a question about this basic notion of being able to reconstruct the signal from the amplitude of the spectrogram, that it actually requires some extra processing. And then we spoke about Shannon and the communication model once we started moving towards the generative models. But before we did that, the notion of encoder, decoder, which we've seen later, and a lot of machine learning talks about encoding, decoding, without actually referring this to the origin of this concept, which is a communication channel. So I think it would be great opportunity in this class to understand what is communication channel, what is information source, what is a channel, basically something that adds noise to the transmission, and a decoder that basically takes whatever the encoding was and translates this. So just understanding and remembering this definition of the basic model. The three Shannon theorems, it's totally, whole class, but if anything from information theory, at least I would like you to know that this is what information theory is about. It is three basic theorems. And we kind of mentioned the relevance of theorem 1, theorem 3 to machine learning, and I'll repeat this in a second. But almost as a general knowledge, right? Entropy as a limit of compression for lossless encoding. So lossless compression, error correction, and lossy compression. Basically, these three aspects of information theory and how they relate to measures like entropy, channel capacity we mentioned, but we never looked into these things because that's really unrelated, at least in the context of what we did with machine learning. We never encountered any error correction idea, but we spoke a little bit about the rate distortion later on. So the idea that you could either represent your code more efficiently, or you can represent it by allowing some error. So kind of remember these three theorems. The notion of entropy, okay, of course there are much more complicated distributions, but this is one good example. So if we had to choose something and be able to ask you something about the entropy, the binary source, understanding where this graph comes from, and basically, it's even, I think, fair game to ask you to compute an entropy for a binary source with some p given, and you can basically plug this into this equation or look it up into this graph and come up with a number. So hopefully, this one example will serve you as kind of a guideline about much more complex entropies. And it shows you basically that fair coin has the highest entropy or unpredictable, and the entropy is 1, which requires 1 bit because these are log 2. So you need 1 bit of information to encode a fair coin. And if you have a coin which is biased to either way, and you look at longer sequences, the information theory tells you that you might efficiently assign for long blocks. And so that's kind of the whole encoding trick. But on the average, you'll be able to assign less bits for biased coins. And this is the number of bits you would assign. So fractional bits, the only meaning they have is really because you encode blocks. So the bit per symbol will be less than 1. So here are the examples. I want you to be able to understand the math here. It's pretty straightforward. So the connection with this and the whole information theory is, of course, the interesting application or the use of this mathematical trick. But at least the math here is kind of very straightforward. We spoke about Markov model. So I would like you to remember what the Markov model is, that this is sort of a finite state machine with transition probabilities. Your state vector basically describes what are the probabilities of being in each of these states, right? So it could be either binary, so 1, 0, 0. It could be distribution. You can have some kind of a fractional probability, so you don't know exactly where you are, but it gives you some likelihood of being in every state. And this is how the Markov works, right? You multiply your state by the matrix and you move to the next one. And that eventually, if all goes well, you start from some initial state and you do infinite iterations, you get to a so-called stable state. Just understanding this concept, understanding the mechanism, we didn't prove anything about, when you reach the stable state, the fact that you can reach, for some condition on this Markov model, you would always reach a stable state and so on. But the mechanism, what the Markov model is, I think very much represented in this graph understanding what this matrix is, or ability to relate these two, one to the other, through these relations. And you did this also in your homework. The Lempel-Ziv algorithm. So really the only thing that I would like you kind of to be able to do, like on a piece of paper from scratch, is do incremental parsing. So if you give you a sequence, you should be able to put commas according to the idea of the Lempel-Ziv, like you did in the incremental parsing homework. So either put commas here or translate, this parsed sequence to a tree, right? We won't ask you to assign the probabilities, but just this relation between these two. I mean, you did assign the probabilities in homework, but that might be just a little bit more of a calculating and weighing. And I mean, we're going to ask you short questions that you can solve in 2-3 minutes. So yeah, we won't go into too much math, but just understanding, remembering how incremental parsing works, and basically how it subdivides a sequence into these continuously growing phrases and relations between this and the tree. The IP continuation, you did this in the homework. We might ask you some basic ideas, to show understanding of how you basically use this tree for music, for generative purposes. So that's kind of the whole musical application of Lempel-Ziv, and that we have been working on, and basically how you use the dictionary to create sequences, which in some sense are samples from the same information source. Talking about the voter, so again, some kind of historical references. Knowing what the voter is, maybe just remembering the date is also kind of at least approximately knowing that it's almost, well, it's 80 years old, right? And the idea that you could create a speech by the spectrum keys, VAS and HIS, kind of understanding this model, which repeats itself then later when we talk about the speech, basically source filter model. So just know what the voter is, kind of remember pretty much where it came from. This other pattern playback, again, refers to the same attempt in the 40s to kind of create synthetic speech. The idea how it worked, maybe not, again, we didn't discuss this in too much detail, but again, we had this sort of a spectrogram plotted on this paper roll, and we had the pitches generated by this tone wheel, okay? So it's just another pattern playback, another device that used a light collector and kind of a spectrogram, and then amplifier that created speech. Very different way, just allow you to plot formats. So this brings us to the notion of source filter model in speech. So I would like you kind of to remember that this is kind of one of the popular in the early models of speech. So I would like you to know what glottal pulses are, what the vocal tract is, and how they're related source and filter. Right? And so, yeah, just a basic production model. These two terms, I think, are the main points from this slide. The notion of formants, we'd like you to know what the formants are. They're basically these amplification frequencies where you have basically gain or higher gain in the spectrogram representation. So these peaks are related to the speech formants, and you have 2 or more formants that can recreate the vowels. So this relation between formants, vowels, and what the formants mean, and this graph only showed you the first 2, and in the homework you kind of played around with this idea of formants and how they generate speech. Yeah, so this concept, formant frequencies and vowels and how they're related, this is something I want you to also kind of keep in mind or take home from this class. We didn't do too much speech synthesis really, although, as I said, like in music and audio processing, I would say we don't want to compete maybe with the actual speech synthesis people, but if you think about singing synthesis or expressive speech, it is definitely something that people in the music department or people who are interested in doing this from CSE and are related in these and interested in these aspects, it's definitely something that is relevant to machine learning in audio, almost in a musical sense. Synthesis with autoregressive filters. Since you had this in your homework, what I want you to, and I didn't put this in writing, so this maybe is a good place to annotate this, but I didn't annotate anything before, so we'll just keep this as a recording in voice. What I meant by putting this slide here and these like code lines excerpt from the homework is understanding what are poles, okay? Actually, there are no zeros, but zeros and poles. So what I'd like you to know is that in filter representation, okay, a pole means basically a resonance or a peak in frequency, okay? I know that we didn't go too much into explaining these relations. I mean, I did cover this in the lecture, but this was really a bit of too much of a signal processing aspect of going between these two. But the idea is that you can actually, this zero pole to time frequency, okay? So, so this would be your usual, sorry, that's the frequency response, okay? And this is the zero pole. So there is this one-to-one relation between zeros and poles as representations. So I would say knowing what a pole and a zero in a filter is, okay? And mostly what a pole is basically a representation in 2 dimensions of some of the filter structures, so that frequencies which are close to the poles have peaks in frequency. So this one. And if you need more help or discussion about these 3 equations here, which is kind of the essential link between structures of filters and their representations, and how it relates to the formats, I think I would like to make sure that you kind of understand what this graph means. So what are the poles? I mean, in the AR filters, we had no zeros, basically, we had only poles. And so these were the resonances. So how you place these poles to get the right resonances. So even just kind of that understanding. Okay? If you want to have a peak in frequency and higher, somewhere higher up in the frequency response, you will move the pole towards the far end. Okay. Or frequencies which are lower, they'll have poles closer to 0 on this unit circle. We mentioned the variable Markov oracle. So what I would like you kind of to understand is this kind of a process of working with audio oracle, where we basically, and this is common to a lot of concatenative synthesis or other ways of manipulating audio to generate a stream. Basically, you extract features, okay, and then you kind of find a way to concatenate the waveform in novel ways to create a new version, or kind of extend like a texture out of this recording. So we mentioned the factor oracle. Again, as I said, we're not going to ask you anything about how the algorithm runs, and in this one we actually did not have any homework on, but I would like you to remember that this is a string matching algorithm, and that it operates by finding suffix links. So in theory, they could be used to generate new sequences by jumping on the suffix links. We kind of mentioned this, I gave some examples. So knowing about the factor oracle algorithms is string matching, and the idea that it actually relates suffixes or finds suffixes in a string for anyone who, and it's usually done, not in any context of audio processing, but anybody who does any kind of string operations encounters various algorithms that actually look for suffixes, so repetitions and suffixes. And the factor oracle algorithm is one example. I would like you to kind of be able to remember this idea. We spoke about hidden Markov models. Again, we didn't have hidden Markov models as such in the homework, but I would like you to know what they are. Basically understand that you have a Markov process with emission probabilities, that each one is basically creates an observation sequence that is a probability emitted in every state. So every state has an assigned output probability. So being able to identify these things and understand what this graph represents, because as one of the really historically most effective ways of analyzing mostly speech, but also in audio or even music. This is a term that I would like you to again take home from this class, and the 3 HMM problems. Right, that HMM solves the classification, the segmentation, and the learning problem. Okay, so again. There are special classes that go through HMM, all the derivations, but the idea is that in these basic 3 problems, that if you have a sequence, you can tell what is the probability that was generated by this model, segmentation that will find you the most likely pass through the states, and the learning, which is the training of the HMM using this EM algorithm that we mentioned, and we kind of discussed a lot in class, but really, proofs of the EM are beyond the scope of the class itself. But this is kind of the learning of the model and the 2 uses of the model, giving you the probability and doing basically this annotation, finding the state sequence, which is sometimes referred to as segmentation. Once you move to neural networks, concept of backpropagation, okay, or differential programming, we kind of mentioned this. So understanding what a very basic neural network looks like, right? And we spoke about this equation that these are weights, and this is the summation, and then each one is actually going through an activation function, which is the sigmoid. So knowing what an activation function is, what are the connections, this matrix of the connections, okay? And then eventually you also need the cost function. So this basic structure, this kind of framework of representing and programming the neural network assignments in some sense, or defining your problem of finding something that maps X to Y using neural network is all summarized here. So at least you know what these concepts are. And we can ask you about any of these basic terms here. The concept of gradient descent, we won't go again to the math. We kind of mentioned this. These 2 slides together will probably end up in 1 or 2 questions, basically understanding what the gradient descent is for. That is basically the way to optimize and find the weights. So backpropagation is done using gradient descent. Okay. And the cost functions. At least these 2, you can at least remember what they are, and remember that this is more for classification and this is more for approximation in a continuous domain, because this is a loss. This is like Euclidean distance. It will tell you how every whatever pixel or sample of an audio differs from some target. Okay, and you do this in Euclidean distance. While here, this will be more like a classification when you'll have a probability of a class. So just remembering what is quadratic laws and cross entropy is a good introduction to later classes if you do neural networks. Okay, sorry, moving forward. Feature extraction. We spoke about this idea that we can decompose spectrogram into activations and basis functions. So the whole idea of feature extraction, unrelated to neural networks, but also eventually done also as an autoencoder in one of the exercises, is just understanding this concept that you can decompose something like a set of spectral beams into templates, which will be audio bases and activations in this representation. So kind of the terminology really. PCA, we mentioned this. These are the main, maybe the first thing about the PCA is what I want you to kind of remember. What PCA does is basically does this kind of a decomposition where it finds the composition that is optimal in terms of this mean squared error. So that's what it does. This is a dimensionality reduction because you have less of these basis functions here. And this is the optimality. I mean, the rest maybe is less critical. It's for your information, how it can be estimated, where it's used, how it's used in audio, how it's called. We did this in the homework. So this is actually the next slide, or this slide now, where I want you to understand why, why they're related and why they're not related. And the idea is that by using activation functions or nonlinear, this kind of a nonlinearity activation in the neuron actually is the reason that we can do deep learning. Okay, we can make them layers and layers and layers, while in linear autoencoder, actually it's just a matrix transformation. So it's kind of a tricky or a little bit of a, once you know this, it's evident and then it's simple, but before you have seen this concept, sometimes it's a little bit elusive. I mean, what is the relation with neural networks and this PCA, which is usually done with this matrix multiplication? So I wanted you to understand that no matter how you call the PCA, if you derive this using the differentiation, you basically approximate the loss function here. By using gradient descent, you eventually estimate the matrix, and this estimation is what we do in both cases. And then I think that kind of allows us to understand, or the motivation or the logic that I was kind of trying to follow. And if it was a little bit confusing or elusive so far, I hope that the summary kind of explains that line of thought was that yes, you could do feature extraction using linear methods like the PCA or KLT, the current law F transform in audio. But once you do this with neural networks, you can have this deep representation, and this is where the feature learning actually got its big boost, that it suddenly allowed us to find features which are much more sophisticated than just doing dimensionality reduction. So this link, I think, helps to understand the context. So, and then we move to the generative problem. So I would like you to keep in mind, maybe this saying, why we want to do the generative approach is that to recognize something, we need to be able to generate this. Kind of remember this whole notion of what a generative problem is, basically taking a distribution, a simple distribution, uniform or Gaussian later on, and map this to more complex distributions. So what is a generative problem? This slide, we can ask you the definition or the basic two notions of these latent state representations and how we use this to generate. And I think a lot of you now actually doing this in your projects. So understanding the concept of a latent space, and this is really specific to what we do. I mean, a lot of neural networks talk about latent spaces, but then don't try to generate. If you want to generate something new, interpolate, walking, this is my term, but we have seen examples of interpolating on the latent space, or in painting, which were more specific, more sophisticated ways of basically doing some kind of a trajectory in the latent space. So understanding this concept, the variational autoencoder Really just kind of the architecture itself, understanding that this is an encoder-decoder with a middle layer, which is a probability distribution. Once you're good with that, I think we covered the notion of variational autoencoder. Now, I mentioned the elbow. This is kind of the technical part. So what I want you to be able to take away from this slide, okay, or what can we ask about the math of the elbow? So you could, you could see here, and we kind of discussed this a lot, that this is basically the name itself, okay? The evidence lower bound. This is a way to approximate the evidence, the log of the probability, okay, with some other distribution Q, okay? So with the trial distribution. So just kind of like if you see this equation, okay, and we can ask you maybe something about the terms here, what they are, or how they relate to the graph above, I would like you to be able to, see these relations, okay, and see that this is kind of a way to, this is a loss function in some sense. This is the way to write the loss function for learning the variational autoencoder, okay? So elbow, the evidence lower bound, is our optimization target for variational autoencoder. The other things which I would like you to remember, I think it's going to be hard a little bit to ask this and make sure that everybody kind of has the right understanding. And I didn't put this in the slide, but really all I referred here is this notion of renormalization trick. Maybe I should have put it here in the slide so we kind of know that you should maybe remember this notion, this term. The renormalization trick is what allows the variational autoencoder to be estimated because it goes through this probability layer, okay? So this one shows this. Maybe we will add here in handwriting the renormalization trick. So you should kind of remember this notion that the elbow is our loss function, and renormalization trick is what allows for the back propagation to happen in variational autoencoder, okay? Here I wrote this explicitly, but it doesn't really, I'm just going to reuse the slide. So you can see here basically how the renormalization trick allows us writing everything here, this part of the loss function, in an analytical way, and then this is being solved in TensorFlow. So we have seen an example actually where this was really programmed in. But the basic notions are these, the elbow, the loss, and the renormalization trick. RNN. Understanding the basic structure of RNN, understanding what are the hidden states, how they propagated, and this notation. If you understand this notation, this is so common to neural networks that once you look into more sophisticated neural networks, you kind of get a sense of how you build with matrix multiplications and activation functions the whole process. And here is the time. So understanding what the architecture of RNN is. Then we spoke about the softmax, or basically many hot activation thing. So I would like you to know what a softmax is, because you used it, and the reweighting with temperature, because it was part of your homework. We spoke about the idea that it's kind of a way to go between totally flat and equally, well, this is the temperature one, so this is the probabilities, but then by playing with the temperature, you either select the top one, slowly you can kind of reveal the next, and the lower peaks become more prominent, so you can use this for selection. And in your homework you did that, so the question will be probably more related to the homework, how you use the temperature. And the idea is that, depending on the temperature, you can generate more nodes in your sequence, or have more variability, because if not, you always be stuck with the highest probability. So the role of temperature in softmax was what I meant before. Moving to generative adversarial networks, the architecture itself. understanding what a generator is, what the discriminator is, and the loss function and the min-max. So kind of just understanding and being familiar with, with the loss function and how it operates, and the idea that we basically alternate between generator and discriminator. So being able to understand and identify what each one of these equations mean on a high level, just basically D as the discriminator output, and 1 minus D of the G of Z is the generator output. So with the discriminator operating on the generator, just making sure that you understand this notation is also really kind of a very common way of, I think I need to move this way. Oh yeah. Sorry, some things here on my screen are related to Zoom, so they're not in the video, but I guess the other one was blocking all the time, and I didn't think about this. So understanding what this means, okay, and how it relates to the architecture. And then I think pretty much done. Did I have something else? Sorry. Yeah, okay, so it looks scary, but let me summarize this, and this is the takeaway point from this whole discussion, which I want you to be able to do is understand. We showed or discussed that in the optimal solution, if we take these functions and we differentiate whatever the process was, we end up with these two different things. The discriminator should be this expression, and the loss for the optimal discriminator basically looks like this. So the loss in the generating discriminator is this. What can I ask about these two equations, this and this? Well, I said this in class, and I'm saying this now again, so that's kind of pretty much the question, is if your generator learns ideally the data probability, right? Can you tell me that the discriminator will be giving me an output which is 1/2, the probability 1/2 for any example? Or in some sense, why the best outcome of the discriminator, if it learned the data, would be that basically with probability 1/2, it will tell me that this example is fake or true, right? And intuitively, yes, because it's 1/2, it means it really doesn't know. It knows that it might be fake. It cannot distinguish, so it can throw a coin, right? So that's intuitively, right? If really if our GAN managed to learn together with the generator the data in such a way that the generator makes ideal or perfect fakes, then the best thing the discriminator can do is just flip a coin and don't look at the data and just randomly decide it's fake or true, because it knows that it could be fake. Now, how is that shown in these equations? Well, basically, if our generator is ideally matching the data, the distance here is 0, right? Or the PG equals PR. So we want this to be smaller. So this is 0. If this is 0, then PR equals PG. And again, there is this inconsistency in notation that that I should point out. P data is PR. So if PR equals PG, this is 0. And if PR equals PG, this is 1/2. Okay. So if you really manage to learn this ideally, then the loss here is 0 and the D is 1/2. And this is what these equations show. So really, this is just a proof that in the ideal case, that's what will happen. Nobody actually tells you that that in practice learning GANs will succeed to reach that level. But it's still kind of an indicator, at least when you see that the discriminator kind of starts running somewhere around the 50%, you see that it's probably learned something. That's it. So that was the course material review. Took me practically the whole class. maybe so I don't restart the video again, before I move to questions, let me kind of also say a few words about the quiz preparation. Okay, as I mentioned, we will open a discussion page, and we moved the quiz after your final project submissions, so you can kind of get one thing out of the way and prepare for the quiz. As I said, it's mostly multiple choice, so making sure that you understand these concepts. If you kind of go through, I think what I kind of explained pretty much points out to the terms and the questions we can ask. So kind of plan on approximately one question per slide, and we have a lot of slides here, so we'll have less questions, right? But I mean, I cannot tell you how many questions exactly we'll have right now. We had almost 50 slides, but we'll have maybe, well, not half, maybe a little bit more than half number of questions that you can complete in an hour and a half. So kind of comfortable number. And no real computations will be required, but we might ask you maybe to verify a number, okay? So, or we can put an equation and ask you what some terms in the equation mean or what they represent. So hopefully this kind of, you know, really like overview of so many different materials that, you know, that lead you towards the ability to think about now taking audio, taking MIDI, and analyzing them, representing them in some way, plugging them into a statistical model, and then banging the statistical model with some other maybe, you know, planned way of triggering these latent states, or some kind of other way of querying this model and generating an output. At least that picture, I think, has been pretty much covered. So, so think about this as a bit of a boot camp, but hopefully, you know, with the boot camp, once you pass it, and if you're not discouraged on the way, you're good to go. So we really kind of like hope that everybody will be able to handle the material. And then once you're good with this, you shouldn't worry about you know, grades or difficulty like that. And I think everybody is doing great so far. So I'm really happy, and there's a lot of discussion going on. So I think it will be good. So this is as far as my kind of review of the materials and the idea of how to prepare to the for the quiz, and encouraging you to ask more questions. And then once we have the discussion page, we'll try to facilitate also the preparation more. So I'll stop the recording and open this to questions.